Hello everyone. Today we shall start with or we shall continue with the design of two-way slab, that is lecture number 35 from module 4. Is the screen visible to you all? Is the screen visible?
Yes, ma'am.
Okay, in the previous session we were solving the design example for two-way slab, that is RC slab for room measuring 6.5 meter by 5 meter, and we have calculated the effective depth there. Then we have also calculated the effective span in both the directions, that is Lx as well as Ly, and make sure that Ly is always the larger span and Lx is always the shorter span. Then we have also calculated the ratio of Ly by Lx so that we can calculate the alpha x and alpha y values. Then we have calculated the loads acting on the slab, that is self weight, live load, and in turn we have calculated the ultimate load. And next thing is we have calculated the design bending moment and the design shear force. And in the calculation of design bending moment, we need to take care of alpha x and alpha y values. That is, they are coefficient values from table 26 of IS 456. We have taken the values of alpha x and alpha y. And the case given in the numerical is referring to four edges discontinuous case. So we have considered the positive moment at the midspan condition, and we have got one alpha x value and one alpha y value. Here there will be no negative moment since we are not considering any support section. Okay, considering that we have got alpha x value as 0.079 and alpha y value as 0.056. And using this, here there in the code book, we have the equation for finding out design bending moment, that is mx as well as my in both the directions, in x direction as well as in y direction. If we consider bending moment in x direction, we need to consider alpha x into wu into lx square. That is the span in the shorter direction. But even though if you consider my also, you need to consider alpha y, but instead of Ly, you need to consider Lx only. So remember, whether it is Mx or My, you are supposed to consider Lx, that is shorter span in the calculation of bending moment. And next we have got the positive moment Mx as well as positive moment My. And the next thing what we had done, what we had calculated is we have checked whether the depth provided is sufficient or no. We have checked for the depth provided. So in order to check for the depth provided, we had considered mu is equal to mu limit. We had considered mu is equal to mu limit. So considering mu is equal to mu limit, and for Fe 500 grade of steel, we have the equation mu is equal to 0.133 FCK BD square. So out of this, if we calculate D, it is 103 mm. And however, we have provided the effective depth as 160 mm. Hence, the provided depth is more than that of the required depth. And
And paper is
now,
not visible.
today's, yes, hello,
Paper is not visible, ma'am.
PDF is not visible. Is PDF
Yes, sir.
visible? Everyone, is PDF visible?
Yes, ma'am. Yes, ma'am.
Okay. Now, today we shall continue with the calculation of reinforcement, that is tension reinforcement. Here we have two types of moments, moment in the shorter span and moment in the longer span. Now, if we consider moment in the shorter span and moment in the longer span separately, we need to calculate reinforcement in both the directions separately. Once we need to consider mx value and calculate the value of reinforcement. Once we need to consider my value and calculate the value for the steel. So in order to calculate, either we can use this equation, which is the equation code book, that is 0.87 Fi ASTD into 1 minus Fi AST divided by FCKBD. Or else we can use the one more equation which we have already used in the design of beams and all, that is AST, where we'll get AST as a single value. Here we'll be getting two values of AST. Out of those two values, we need to consider only one. So you can use even the equation AST is equal to 0.5 FCKBD divided by Fy into 1 minus square root of 1 minus 4.6 mu divided by FCKBD square. Either of the two equations you can consider. Now, let's consider the steel in the shorter direction first. Let's consider the steel in the shorter direction. If I consider the steel in the shorter direction, that is referring to ASTX, that is the value which refers to mx value. So mx is nothing but moment in the x direction, 28.4 kilonewton meter. So that's 28 into 10 to the power of 6 we have considered in order to convert kilonewton meter into newton millimeter. Sirish Kulkarni, mute yourself. Sirish Kulkarni, mute yourself.
Yes, ma'am.
So here, in order to convert kilonewton meter to newton millimeter, we need to multiply mx value with 10 to the power of 6. And here all the values are substituted as known, and only the unknowns are AST. Now here we have a quadratic equation. Out of the quadratic equation, we get two values of AST, and we need to consider the best value what we can provide as an reinforcement. So here the ASTX value turns out to be 438 mm square on and around. So 438.438 mm square is the steel amount of steel in the x direction. So in order to find out the spacing between the steel or spacing between the bars, we can assume the diameter of the bar. We can go ahead with either 10 mm or 12 mm depending upon the of steel diameters. So here we have considered 10 mm diameters to, sorry, 10 mm diameter is reinforcement, and we can calculate the spacing using this 10 mm diameter bars. That is ASTX divided by pi by 4 into 10 square, that is area of 1 bar into 1000. So why we need to multiply 1000 is in order to make sure that we are designing for 1 meter width of the span, and the same reinforcement is continued for all other span. So it is 10 mm diameter at 175 mm center to center. And in the similar way, we are going to calculate the steel along the longer direction. We need to consider the steel along the longer direction, that is My. So My value is 20.13 kilonewton meter, which is already been calculated. Now instead of mx, we'll substitute My and calculate the value of AST. So AST turns out to be 327 mm square. 327 mm square. So in order to get the spacing of the bars, assuming 10 mm diameter bar, we can have area of one bar divided by AST required into 100. And what we get is 241 mm. So what we can write is 10 bars at a spacing of 240 center to center. They are placed along the longer direction. They are to be placed along the longer direction. So with this, we can find out what is the amount of steel provided. Now the required steel amount is, for shorter direction it is 438 square. For the longer direction it is 327 square. And we need to calculate the provided values so that it will be easier for us to calculate the shear criteria. And shear, check for shear and the development, and make sure that whenever you are checking for the shear, always you need to get no shear reinforcement requirement. You need to get no shear reinforcement requirement. That is, K into tau C should always be greater than tau V. Suppose if you get tau V more than K into tau C, make sure that you redesign your section or you recheck your design, because in the case of slab, you are going to get K into tau C value always greater than tau V. So with this, the last part is check for the deflection. So in the check for the deflection, what you need to calculate is L by D actual is less than L by D permissible or L by D allowable. So L by D allowable is equal to L by D basic into K1 into K2 into K3, where K2 and K3 they refer to the compression reinforcement modification factor and the modification factor for the flanged section. So those will not be applicable since we have not designed for the compression steel. So K2 and K3 will be equal to 1. So only the modification factor we need to find out is K1. That is, depending upon the figure, we can find out the value of K1. And we can find out the value of Fs equal to 0.58 Fy into area of cross section of steel required divided by area of cross section of steel provided. And already percentage tension reinforcement would be calculated while calculating the shear reinforcement or check for shear. Then we can just get the modification factor by projecting horizontally. And we can just find out what is the allowable value. Here the allowable value is 39 and the actual value is 32. So hence what we can say is actual L by D is less than allowable L by D. Hence the safe. Hence the design is safe. So with this, the calculation part for the design of two-way slab ends. Design of two-way slab end here. Now, let's proceed with the detailing. Before proceeding with the detailing part, let me go ahead with one more example and then go with the detailing part so that it is clear for you all regarding the two-way slab. Now, in the two-way slab, we have considered the case of case 9, that is 4 edges discontinuous. 4 edges discontinuous. Now, let me consider the next example. So let's consider one more numerical example for the design of slab. We'll just go through this and then Later, we'll go ahead with the detailing part in detail, both one-way slab as well as two-way slab. Now, here you can see, design the slab for a room of clear dimension 4 meter by 5 meter and width of support is 300 mm and the condition given here is two adjacent edges discontinuous. Live load is 3 kilonewton per meter square, full floor finish is 1 kilonewton per meter square and materials used are M20 and Fe415. Show the reinforcement details for the span. Now, first and foremost, what we'll do, we'll note down the data given. And next thing is to check whether it is to be designed as a one-way slab or two-way slab. So can you tell me how we can decide whether it is one-way slab or two-way slab? Can you tell me how should we consider one-way slab or two-way slab?
LY by LX, ma'am.
Ly by Lx ratio. Ly by Lx ratio means always the ratio of larger span to shorter span. 5 meter by 4 meter. So in order to decide the type of slab, we'll get the ratio Ly by Lx is equal to 5 by 4 is equal to 1.25. And this 1.25 is less than 2. If the ratio of Ly by Lx is less than or equal to 2, we need to design it as a two-way slab. So we can decide that it is a two-way slab. Next, we need to find out the dimensions of the beam now. Sorry, slab. In order to calculate the dimensions, what we'll do? We'll assume again span to effective depth ratio as 26, considering it to be here two adjacent edges are discontinuous. That means two edges are continuous, two adjacent edges are discontinuous. So considering continuous criteria, we'll assume a value of 26 and we'll get the depth as 0.153 meter. So what we can consider is, we can consider the effective depth as 150 mm and considering effective cover of 25 mm, we can get the overall depth as 175 mm. And next thing is to calculate effective span from the codal provision, that is 22.2.B1. So Lx value is center to center distance between the supports, 4 meter plus half on the left hand side, half on the right hand side. So it will be 4.3. And Ly 5 plus 0.3 by 2 plus 0.3 by 2. Or else what we need to consider is plus effective depth. So depending upon the criteria, we need to consider Lx and Ly ratio. And once we are done with Lx and Ly calculations, next thing is to go ahead with the load calculations. Self weight, that is overall depth multiplied with unit weight of RCC. Floor finish is considered as 1 kilonewton per meter square. Live load is 3 kilonewton per meter square. And the total is 8.375 kilonewton per meter square. So, and the total factored load, when we multiply partial safety factor, it turns to be 12.57 kilonewton per meter, considering per meter length. And next thing is to calculate the ultimate moment and the shear value, that is design moment and design shear. So in order to calculate that, Ly by Lx ratio we are going to consider, and it turns out to be 1.23. And let's proceed with the table 26. Here in the table 26, two adjacent edges are discontinuous. So let's consider two adjacent edges discontinuous. Two adjacent edges discontinuous here, that is case 4 from table 26. In this case 4, we have negative moment at the continuous edge as well as positive moment at the midspan. So there will be two values of alpha x and two values of alpha y. That is short span coefficient and the long span coefficient. So we need to consider this. And what is the value of Ly by Lx? Let me see. Ly by Lx ratio is 1.23. So if Ly by Lx ratio is 1.23, the value of alpha x lies between 1.2 and 1.3. So we need to interpolate and get the value of alpha x for Ly by Lx ratio equal to 1.23. So for 1.2, the ratio alpha x value is 0.06. For 1.3, it is 0.065. So we need to calculate the value for 1.23. So by doing the interpolation, we are going to get the alpha x value as 0.0615. And in the similar way, by interpolating, we get the alpha x positive value, that is 0.0462. So two values of alpha x and two values of alpha y will be seen here. So let me, alpha y value need not interpret because what may be the Ly by Lx ratio, alpha y value remains the same, that is 0.047 and 0.035. And only the interpolation is to be done for the alpha x value. So once we are done with the coefficients, next thing is to find out the design moment and the shear force. So here positive alpha x, positive alpha y, negative alpha x, negative alpha y. So there are four coefficients, hence we'll be having four moment values. Positive mx, negative mx, positive my and negative my. And the corresponding coefficients are used in order to calculate the moment. And whatever may be the direction, whether x or y, the span to be used is Lx only. So positive mx, negative mx, positive my and negative my values are being calculated. Positive at the midspan, negative at the continuous edge. And the next thing is to find out the ultimate shear force, that is design shear force. The design shear force for the two-way slab is to be calculated using the equation Wu into R raised to 4 divided by 1 plus R raised to 4 into Lx by 2. And where the value of R is nothing but Ly by Lx ratio, that is 1.23. So this is how we need to calculate the shear force value, that is 18.85 kilonewton. Now, once we are done with the design moments and the shear force, next thing is to check whether the depth provided is sufficient or no. In order to check for the depth provided, either we can use the step which we have done in the previous numerical, that is assuming mu is equal to mu limit, calculate the depth. If that depth is less than the depth provided, then we can continue with the design, or else calculate mu limit considering the depth which you have provided as done here. And if this value of mu limit is more than mux as well as muy, that means all the four moments, then we can say that the depth provided is sufficient. We can proceed with the design. And in order to find out the amount of steel in the next step, that is the main reinforcement, what we can do is we can use the equation as we have used in the previous design, and we can calculate the value of AST. If there is positive MUX, the corresponding steel will refer it to as positive ASTX. And if it is negative MUX, then we'll consider corresponding reinforcement as negative ASTX. And in the similar way, we'll be considering for the Y direction also. So here we have ASTX as 204.17 mm square as well as 274.4 mm square. Now we need to consider this value and compare it with AST minimum. So in order to calculate AST minimum, as already discussed, we need to check whether it is a HYST bar to be used or mild steel. If it is HYST bar, AST minimum is equal to 0.12% of BD, and if it is HYST, if it is bar, it is 0.12% BD. So if the AST minimum value is more than AST calculated, then AST minimum value will be used in the design. Otherwise, the calculated value will be used. So hence, here the relation is being shown, and ASTX, positive ASTX will be AST minimum because ASTX calculated is less than AST minimum, and negative ASTX is same as that of calculated value. Now, once we are done with AST minimum calculation, next thing is to proceed with positive ASTX reinforcement. So we can consider the diameter of the bar as 8 mm or 10 mm depending upon the amount of reinforcement. Here we have considered 8 mm bars. Considering 8 mm bars, the spacing is to be calculated, that is cross-sectional area of one bar divided by ASTX into 1000, that is 1 meter span. The spacing will be 239.3 mm. And similar way for the negative ASTX, it will be 183.1 mm. So we can consider for the X direction, 8 mm diameter bars at 225 mm center to center as positive ASTX, and 8 mm diameter bars at 180 mm center to center at negative ASTX. So this is how we need to calculate the reinforcement details. Similar way, we need to consider the Y direction. In the Y direction also, similar way, we'll be calculating positive ASTY and negative ASTY and provide the reinforcement bars. That is 8 mm diameter bar at 300 mm center to center and 8 mm diameter bars at 225 mm center to center. And next thing is shear reinforcement. In order to calculate shear reinforcement, as already said, K into tau C should be more than tau B. So let me check whether this criteria is being satisfied or not. So in order to make sure that we'll be comparing tau V with K into tau C. Tau V value is BU by BD. So it turns out to be 0.125 Newton per mm square. And PT value is 100 AST provided divided by BD. Here in case of AST provided, there are 4 AST provided. 2 in the Y direction, 2 in the X direction. So what we can consider is the maximum AST where we have or maximum moment. Here we have 10 kilonewton meter, 14 kilonewton meter in the X direction, and in the Y direction we have 8 and 10. So what we can consider is 14 kilonewton meter as the standard, or this is the value which we have maximum. So negative AST X value is to be considered. Here, corresponding to negative ASTX, we can find out AST provided and we can get the value of PT, that is 1.186. So corresponding from table 19, we see as 0.3, and this K into tau C value is more than tau V because tau V is 0.125 Newton per mm square. Hence, we can say that there is no shear reinforcement required and the slab is or the design is safe in shear. And the last part is deflection. To prove L by D actual is less than L by D permissible or L by D maximum. So L by D maximum is to be calculated from the basic criteria as we have done in the previous designs, design of beams or slabs. And we can compare here and we can say that L by D actual is less than L by D maximum. Hence the design is safe under deflection. And now the next thing is torsional reinforcement. Torsional reinforcement. As we are using table 26 of IS 456, here we have the provision for torsion at the corners. We have the provision for torsion at the corners so that the corners are not lifted up. So in order to make sure that corners are not lifted up, we are going to provide the torsion at the corner. So in order to provide the torsion at the corner, how much torsional reinforcement is to be provided? So if it is a discontinuous edge, it is 3/4 of the AST maximum. If it is a discontinuous edge, it will be 3/4 of the AST maximum. And if it is a continuous edge, it will be 3/8 of the AST maximum. That is torsional reinforcement. So what we can write is 8 mm diameter bars at a spacing of 225 mm center to center. If it is a discontinuous edge. And if it is a continuous edge, we can refer to as 3/4 or instead of 3/4, we can refer to it as 3/8 of the AST maximum. And we can calculate the diameter as well as spacing of the bars. So this is how we need to proceed with the design of two-way slab. So in the first design of two-way slab, there was only positive moment because all the four edges were discontinuous. And in the second example, we had both positive moment as well as negative moment. Since we had both continuous edge also as a part of design. That is, the case was two adjacent edges discontinuous. So depending upon the number of coefficients, we'll be getting the number of moments and accordingly we can calculate the reinforcement. So that's all for today. Thank you. If you have any doubts, you may please ask.